So this is a video on the differential geometry and especially on the topic one forms. So these topics are very important when we're trying to understand the general relativity, as all of general relativity is based upon the differential geometry. That's why it's very important to know about these stuffs, as I have taught different types of things like the basic things of Christoffel symbol in my YouTube channel. So we are going to discuss about the differential geometry also, but this is not a very core theory video. Okay, so I'm going to just a little bit talk about it, what exactly is one form, and then we are going to derive, you can say, the proof of the representation of the differential one form. So let's see how we are going to do this. First of all, we have to define that what exactly is the differential one form. So differential one form is you can generally view as the covector. Yes, differential one form can be viewed as the covector, and I hope so that you know about what is a covector. So covector are nothing, they are the linear functionals. Linear functionals. What is the meaning of this? I mean, if you're confused by this, then the simple meaning is that this particular covector takes an element from the vector space and then transforms it into a real number. Yes, that is the meaning of the covector, and another name is the cotangent vector. So these are the different names, so don't confuse, they are all the same. And that is the basic meaning, that covector takes an element. So here I'm going to write element from the vector space and transforms it into the real number. So it's like the mapping, and that is the meaning of covector. But more especially, if you want to know about that, what is one form, then you can think that one form is a covector field. Covector field. Yes, in most of the books you will see that it is written as covector, but the more appropriate answer can be a covector field. Just like for vectors you have vector fields, for covectors you have covector field, and that is the one form. So this is the basic idea behind the one form, covectors and the linear functionals. So the meaning of linear function means that there should be linear in our argument, or you can say that it must follow the Leibniz rule. Okay, so this is all about the one form and covector field and all that stuff. These are not very hectic. Okay, so now the next topic is going to be on the you can say the representation. First of all, before representation, I'm gonna write some of the very important points about this particular one form, and it is represented as, first of all, represented as generally d of f, differential of a function where the function that you have chosen, it is very important, the function that you have chosen is real valued and it should be a c infinity. So what is the meaning of c infinity functions? The meaning of this is that it should be a smooth function. This is the idea behind the differential, and the fact is that differential also acts like an operator. So the next point I'm going to do is they act like operators. They act like operators. Just like the tangent vectors act like the directional derivative. Okay, and third very important point is that when you apply this particular differential to a vector, to a tangent vector, and this is exactly same as the acting of the vector, tangent vector, on a particular function f, and this is exactly equal to the directional derivative of that particular function in the direction of the tangent vector. Okay, so don't confuse, I will try to explain all of that stuff. This is written as f. Let me clarify it. This is f. So what is the meaning of this, what I have written? So here, if you have carefully done the part of the tangent vector, you all know this particular equality. Yes, these types of equality are taught in the differential geometry, or in first class of differential geometry about the tangent vectors. Okay, so this is quite familiar, but I'm going to express this. I'm going to try to explain this also. So the meaning of this is that when you try to, so listen it carefully, when you try to operate, let's say we have a vector, tangent vector at point P and a function there. So when you try to act this particular tangent vector on a function that is defined, and the function should be very important, function should be a smooth function. Smooth. Okay, so here in this particular scenario, see that when you try to apply this particular tangent vector at point P to a function, it is exactly equals to the 1 minute. Sorry for this. Okay, so this is exactly equals to the directional derivative of that particular function in the direction of the tangent vector. Okay, so what I have said you might have confused, but let me clarify that if you have understood that if you have taken the class of the vector calculus, you know that what is the you can say gradient of a particular function is. So the gradient of a particular function tells you about how the function changes when you move. So it is exactly like that. When you try to operate this particular tangent vector to a function, it is equals to the directional derivative of that particular function in the direction of x, in the direction of your tangent vector. And that is the exact meaning, and that's why this equality is very much more important. But there is also hidden truth about this. What? So remarks. There is something that I want to tell you, that this shows, okay, this shows that tangent vector is a operator, and yes it is, okay, is an 1 minute, is an operator. And yes, exactly this is the case. There is also a very important representation of this. Okay, representation is that the tangent vector at P is defined as the v of I del by del x I and at point P. So this is a representation. As you can see that it is represented in the form of derivative, and that's why when you apply, so here's third point, that's why when you apply the function, it is equals to the v of I del of f divided by del of xi at P, in the direction of P, and this is exactly equals to the directional derivative of that particular function in the direction of x of P. Okay, this is a quite very useful result. This is a quick proof. You can derive it on your own, and if you want some reference, I'm going to recommend you a particular book which is not I don't know that it's famous or not, but it is very useful for physicists because it's meant for physics students. So it's Differential Geometry. I 1 minute, I guess it's the name of like a Differential Geometry by the name, I'm quite not familiar with the name, but I will put in the description box if I find the name. So here you have to pay attention that we have proved a very important result. Now we are going to prove another thing, which is that here another thing, that the differential d of f is represented as one form is del of f divided by del of xi and here is d of xi. This is a representation of the differential one form, and we are going to prove this, and that was our main motto for this particular video. So let's start. Remember what I have written here, which is this particular, yes, remember this particular equation, this particular equation. This is very much important equation, and we are going to use this particular equation to generally contradict our fact. Okay, so in this particular video, first of all, I'm gonna choose this, that I'm gonna say that yes, this exists, this is true, and then I will try to operate this on our vector field and see if the result matches or not. So what I'm going to do is that if I will operate d of the differential on the vector, tangent vector, so it is equals to applying del of f of xi and d of xi, and here the formula of the tangent vector was v of I del divided by del of xi. Okay, so if I take out this particular vi, you will have del of f and yes, in the direction, in the p direction. Okay, del of x I, you have this, and you have this chronicle delta. 1 minute, I have chosen the same indices which is a very huge mistake. So it should be vj. Actually, when I will evaluate it, it should be equal, but for you I'm gonna write it as like different. So here vj del by del x upper index j. And here, if you see carefully, that the basis vector of the tangent vector and the cotangent vector or the covector are dual to each other, it means they form the chronicle delta. This is a very well important known fact, that dx, dx upper index, oh what, okay, so this differential, it means the basis vector for our cotangent space, and if we will try to multiply with the basis vector of the tangent space, it is equals to the chronicle delta. Let me choose a different indices. I have again chosen the same, let's say x of j. So it is equals to the chronicle delta I and j. 1 minute. So it is equals to chronicle delta I of j, and the meaning of this is that they are dual to each other, and that is a very important fact. I'm going to use this. If you will see, we have this and we have this. When we will multiply this, we will get chronicle delta I j, and here should be j. So this is fine, and finally here p. So this is our equation, and if you see carefully, that in the property of the chronicle delta is that if I is not equals to j, it should be equal to 0. But if it is equal to 0, it will not be well defined. That's why I will choose I is equals to j. So if I will choose I is equals to j, it means it is become vi, and this will become 1 if I will choose I is equals to j, and it will be like del of f divided by dxi in the direction of p. And guess what is this? This is exactly equals to the directional derivative of that particular function in the direction of x, or in the direction of the tangent vector. So yeah, we have proved it by the contradiction. First of all, we assume that yes, it is right. First we assume that it is right, and we follow all the steps, and if we got right, then yes, it is right. So this is our equation where we have derived it, that yes, this particular representation is correct. Okay, generally the contradiction is not right, but in this particular case the contradiction is right, as there are different other methods to prove this particular formula, but this is the general method by the contradiction. So this is the particular video, and in this particular video we have discussed a lot about the differential geometry. Not a lot, but yes, a core concept and a core formula, or you can say a theorem. In the next video I will try to make again a short video on the different types of another theorems in the differential geometry, and basically more about the tensors, that what exactly are tensor. Most of the people say tensors are yes, tensors like the matrices and all that stuff. No, a tensor is like more fundamental than what you have studied in the different physics branches, or what you have studied a general typical formula of the representation of the matrices, row and columns. No, that's not right. Actually, if I will tell you in a brief about what is tensor, so tensor is like a machine which takes a covector and a vector and transforms it into a real number. Yes, that is it. That is the meaning of this particular tensor. It maps. If you want to write down in the mathematical form, it is equals to the tension, and it maps from, let's say, cotangent spaces and tangent spaces. So if you know the formula for the representation of the tangent space, let's say TP and TP bar, or you can star for the, and you can extend the idea from TP1, TP2 and all of that, and it spits out, as you can say, that the output is a real number. So this is in the language of the function. The main thing is that it takes a covector and a vector and transforms it into a real number, and it is a bilinear function. It is linear in its argument. It is a bilinear or bilinear sorry bilinear function in its all argument, and that is also a very core concept. Tensor is a very more fundamental quantity than a silly representation of the matrices and the columns, and we are going to deal with this in the next video. So thank you for watching this particular video.